everyone, it's me again, Miss Crane, and I'm here again for round 2, chapter 15 now. I figured I would try and get it out to you guys tonight so you had all day tomorrow to look over any of these notes, rewatch any of the videos. I've already noticed that our video has had a lot of views, and I've gotten great emails from some people that have never been able to come to a review session, so that makes me really happy that I saw all these views, so I'm even more happy to make this other video even though I had already promised it to you. So let's get this started right off the bat. Again, if you want to get out your chapter 15 workshop, I will give you a few seconds to rummage through and try to find it. I know you can just pause the video, right? So it's not that big of a deal, but try to get that out right now, and we're going to go through some of these chemical equilibrium. This is where we're introduced to the ice charts. Unfortunately, yes, they do get a lot worse, and these are just basic ones, but we should be able to go through. I'll give you hints like I always do to try to get you, better prepared for the test. And if you don't understand any of the concepts, hopefully this will clear it up. Okay, so hopefully by now you have some of this out. We'll go through all of the important concepts. Okay, so chapter 15, number 1. Write the expression for Kc. So that's the equilibrium expression, is when you're writing it for Kc. For the following reactions, in each case indicate whether the reaction is homogeneous or heterogeneous. So here we have, for part A, it is, the equation is HF, and equilibrium expressions typically have this double-headed arrow, H plus, and everything is in aqueous, so we know all of it is going to be going into our expression. Now, one thing to note is that if you have a Kc or a Kp, you are finding essentially the same thing. And what do these mean? C stands for concentration. Some of you might be like, well, I see Kc and I see Kp all of the time, but I'm not really sure what the difference is. You find expressions exactly the same way, so that's very similar. But P stands for pressure. So sometimes you'll be given pressures, and that applies also to the ice charts that you make. Sometimes you'll be applying a pressure versus a concentration. So, of course, your ice chart should be all concentrations or all pressure, not, mixing of the two. But you're going to be finding ice charts and these Kc, these equilibrium expressions, exactly the same way. So don't get confused if you see one's a Kp and one's a Kc. And you'll also see later in this demonstration that in this workshop we actually have an expression that relates these two, and we'll get to that. So anyway, it's asking us to find the Kc expression. So basically we're doing, and these are all aqueous, right? We don't write anything that are solid or liquid. You only write aqueous and gases. So these are all aqueous, and they will always write that on your actual test. So don't freak out and think you have to figure that out. Now, when we write these Kc expressions, they're a little different. Don't get them confused with the rate laws. These are always, because rate laws only use reactants. This actually uses concentration of the products over the concentration of the reactant. So you'll be using this the whole time. And this is the only thing they really wanted you to find. They didn't give you any concentration values to fill in here. All you really needed to do was find that expression. So part B, I won't do the last one because this is monotonous. But part B, and again, this one's slightly different. Ag plus Zn 2 plus double-headed arrow. And to give myself more room, 2Ag, these are the products. I'm just writing them underneath. Zn, this is a solid. Ag starts out as a solid. So I should have written the actual states here, because this is a solid, this is aqueous, this is aqueous, this is a solid. So I stated here, you can see that I actually put solid next to the ones that were solid. The only thing you're going to put in your expression are the aqueous. So you should say solid, aqueous, aqueous, solid when you're writing this out. So when I write my Kc expression, it's going to be products again, Ag plus concentration, products over Zn 2 plus. Now, what didn't I add? I didn't add a superscript. So when I actually write this Kc expression, this stoichiometric coefficient actually comes up here, and we make it a superscript. So that's very similar also to what you saw with the rate laws. So again, you follow that same thing. If it has a stoichiometric coefficient out front, you raise it to that power. So that's the only trick. And remember, you will never have in your expressions, you will never have a solid or a liquid. So write that somewhere, ingrain it in your brain, because you will never have a solid or a liquid in your equilibrium expressions. Only aqueous and gases. So that's something you'll have to look for when you're actually evaluating these expressions, right? Okay, so some of these first couple of things are fairly easy. This next one is also just a concept that has to be memorized, which is good and very easy, and even the next question, number 3 after that, is fairly simple to follow. So as long as you know these, should be ones that you get full credit on the test. So number 2. When the following reactions come to equilibrium, does the equilibrium mixture contain mostly reactants or mostly products? So this is just something, like I said, something to memorize. The only thing I have to look for number 2 is what my Kc values are. Kc value here is very, very small. When Kc is much less than 1, so very, very small, when Kc is small, it's going to go towards reactants. And obviously, they give us the opposite situation in B. B shows 2.5 times 10 to the 9th. So that's very, very big. So when Kc is much greater than 1, it goes mostly towards products. Okay, so that's all you're really looking for. You're looking at the magnitude of the Kc values. So my Kc value in this case is very, very small, and my Kc in this case is very large, right? So that's exactly what I'm looking for. Super simple concept, and should be something that you get full credit on in a test, right? Super fast. So number 3, moving on. So look at your number 3. At 1000 K, my Kp is equal to this. My Kp is equal to 1.85 for this reaction. And now they're going to give us a bunch of different questions. And again, fairly simple. So once you get these, you guys are going to be like, oh God, I can't believe I even thought that was confusing. So the first thing they do in this is actually write out the full-on expression. Now, if you know exactly, and you'll see what I mean when I'm actually writing these out, if you know exactly what's going on, you don't really have to write the expression. So you'll see exactly what I mean. For this first one, they're talking about all pressures. It says my Kp value is equal to 1.85 for the expression SO2 gas plus 1/2 O2 gas. And this all double-headed arrow, again, equilibrium expression, have those. SO3, and that is also a gas. Okay? So, again, our first couple of problems were all Kc related, so that was our concentration equilibrium expression. This is our pressure equilibrium expression. So that means we're going to write it like this, Kp, and I want to write this so you guys see it and you don't get confused by it. So it's exactly the same thing as concentration, so don't get that confused in your head. But you write it slightly different. You say, again, it's exactly the same thing. Products over reactants, we take these coefficients out front, we raise them to that power, right? So it's exactly the same thing, but now with pressure, we actually write pressure instead of concentrations have those brackets, right? Can't really see my hands. They have brackets around it. So here, instead of having brackets, since we have a pressure, we say P for pressure. Pressure of my product. Now this coefficient, there's no coefficient out front, so technically it'd be raised to the 1, right? But we don't write that. Now, all over pressure of my reactants. Same thing. Don't get confused because it's a different variable. A lot of people do. P, SO2. Again, my coefficient is just 1 out front, so that's a 1. Don't write anything. P of O2. Now, you're probably not very familiar with raising something to the half power, but it is very possible. And even if you looked over my chapter 14, remember when we had a chart that we found what those superscripts were for a rate law? So you know what I'm talking about if you actually went to chapter 14 and read it. That's the same thing here. If you get a 1/2 for your A and B or your superscripts, finding it from that chart, it's the same thing. You can get you can get a half for a superscript. So don't get confused if you're like, wait, can I get 0.5? Yes, you can get 0.5 or 1/2 of a power for a rate law or for this. So I hope that makes sense to you. If it doesn't, just send me an email. So basically, it did not ask me to write this, but I want you guys to see how it varies from concentration. Concentration would literally just have the brackets around. Pressure has the P's. Okay, hopefully that's less confusing if you were confused by it, right? And they said my KP was equal to that 1.85. It didn't say for me to write this. I'm just showing you. Part A is now something I need to evaluate. Part A, it says, what is the value of KP for the reaction? So in this part, what they end up doing is they swap. So I'm not going to write that out because you can see it from your actual workshop or you can view it online. They take this product and they make it a reactant, right? They literally take this and they swap it. So all of this becomes a reactant, all of this become products. So that's what they do in part A. And they ask me, what is my value of KP? When you literally just swap the equation, you just take 1 over whatever my original KP or KC value. In this case, it's KP. So that's all there is to it. 1 over ends up equaling 0.541. So that's all you do. If they give me a KP value, they swap these values. They make this reactant, these products. Then I just put 1 over. Okay, it's as simple as that. Part B, what is the value of KP for the reaction for this? So in part B, what they do is they end up multiplying this whole reaction by 2. So you'll see in part B there are 2 SO2 molecules. Now 2 times 1/2 is 1. There's 1 O2 and then there's 2 SO3 molecules. So they multiplied the whole thing by 2. When they multiply it by 2, that just puts a 2 out in front. It times whatever value is right here by 2. So hopefully that makes sense. Now all I do to my KP value, if I multiply this whole thing by 2, then I take my 1.85 and I raise it to that power. And that's the answer for B, is literally taking that value and raising it to the 2. Right? So, in that case, fairly simple as well. Now, if I multiplied everything by 3, I'd raise it to the 3rd power. Make sense? Hopefully it does. I don't think that's too hard of a concept to follow. Now, for part C, this is where we're actually using the relationship between KC and KP. And I want to note to you, sometimes they'll throw in KC and actually ask you to find KP, and it'll be really worded and you may miss it. So don't mess up or miss what you're looking for. Make sure you read every problem carefully. So in part C, what is the value of KC for the reaction in part B? So in part B, we found my KC to equal that 1.85 squared, which was equal to 3.42. It says, what is the value? So in part C, it's saying here, what is the value? Oh, sorry, this was KP, excuse me. Hopefully that didn't confuse any of you. So for this whole problem, it's actually been talking about KP, correct? So now it's saying, what is the value for KC? So there's a relationship, and it should be given to you on your test, but you obviously need to know how to use it. So this is what you will be given on your test, but you need to know what everything stands for, right? Equilibrium expression with regards to pressure, equilibrium expression in regards to concentration. R is that gas constant, T is temperature, delta N is the change in moles, and we'll discuss how to get all of those values. So, if you want to, again, I always give this option, you can just leave it like this, plug in for everything and find what you need, or you can solve with in regards to KC. So you can bring KC out and put KP in. Either way is completely fine. So I'm just going to leave it as is because that's my favorite way to do it. So we know my KP value. It's saying with regards, the question says what's the value of KC for the reaction in part B. So we have to use the KP value that was given in part B. So that means 3.42 is equal to, we're looking for KC. Now, our R is a gas constant. Right, you guys have seen that before with PV equals nRT. And then temperature is always in Kelvin, and they give it to us in the problem as 1,000. And now all we need to find is that delta N. So, looking at this, all of that makes a lot of sense. Where does delta N come from? Well, I took the reaction down because I've been writing on every single page. But let's rewrite the reaction. Oh. This is for... Okay. We're looking at part B, correct? So I was writing the original reaction. Part B's reaction, because I multiplied everything by 2. Right, so this is the reaction we're looking at, not the original one that was given in the very beginning of the problem. So here, now, delta N depends on the moles, the number of moles, change in moles. So we're looking at these values right here. So delta N would be my product moles minus my reactant moles. So there's 2 over here. How many moles are over here? This has a 1 out front, right? So that's 2 plus 1, so 3. So my value for delta N is -1. Again, let me reiterate in case that was confusing. Your delta N comes from your coefficients that are out front each of these molecules. So there are 2 moles, and it's always products minus reactants. Always think of these expressions as products over reactants, products minus reactants. So we're going to say there's 2 moles of product minus 3 total moles of reactants. So that's where I get that -1. So you plug this all in, 3.42 equals Kc. And that's all to the -1. So, in essence, you can solve for Kc, right? And your Kc value should end up being 281, okay? I'm not going through the math because it's fairly simple. You multiply these 2 together, raise them to the -1, and then this whole value here gets divided by 3.42. Okay, so I hope that makes sense. And that's the relationship. You will be using that at least once on the test. That's a relationship between Kp and Kc. So if you're given a Kp, you can find Kc or vice versa. Okay, so not too bad for the first few questions, right? Now, number 4, not too bad either. You just have to know what to do. Consider the equilibrium. So basically here, they're giving me 2 expressions to work with, and they want me to come up with a final expression. So in the problem, if you look at your piece of paper, or wait for me to reiterate it, it states, consider this equilibrium. Calculate the equilibrium constant Kp for the reaction given the following information. So these are all gases, so we are going to calculate for Kp. Yes. Okay. So here we were given, in the problem, they're giving us these two reactions. So I will write these out. NOBR, okay? And then 2NO. And everything is in the gas phase. They gave us these two reactions together, and each of these correspond to a Kc value. Kc equals 2.0. Hopefully you can see that. Sorry, it's small. And then Kc here is equal to 2.1 times 10 to the 30. So that's 2.1 times 10 to the 30. So in the actual problem, it says consider this equilibrium. So we actually have to find this from the two that are given to us. So how I teach people to do this, it's fairly easy. I always look first at the reactants. I have N2O2Br2. I need to manipulate these equations in order to get this one right here, okay? So, if I want to do that, I want to make sure N2s are all on the reactant side, because when you add these two together, all the reactants stay together and all the products stay together. So I want N2 on this side, I want O2 on the reactant side, and I want Br2 on the reactant side. So if I look over here, Br2 is on the side that I want it to be. Perfect. I'm just going to leave that first one the way it is. This one, though, so this is my reaction 1, this is 2. This is what I want to get to. This one, on the other hand, should probably be switched. And remember what I said, if I swap an equation, then I need to take the Kc and I have to say 1 over. So, I'm going to swap this equation, N2 plus O2, so this is going to be number 3. N2 plus O2 equals 2NO. So I swapped it. All I need to do to this Kc is say 1 over this 2.1 times 10 to the 30. Okay? That 30 is probably a little easier to see. Okay. So now I have all of these, all the reactants on the reactant side, which is exactly what I wanted. Now, I also, which normally will happen, if you get all the reactants on one side, you can probably figure out what the products, that the products are going to be on the right side, the correct side as well. So as I see, the product over here is the product that's down here. So I'm probably be able to add these together and see that they work together. So I'm going to add together, number 1 and 3 and see what I get. And it should end up working out. So number 1. This one just takes a lot of writing. So forgive me for taking a while. 3 and 2 plus O2. 2NO. Okay? So let me go ahead and add these together. And it should, this is what I want, right? It should end up equaling that. So we have, let's just put them all together. N2 plus O2 plus 2NO plus Br2 all equals all of my products. 2NOBr plus 2NO. Trying to write it big enough so everyone can see. So now, on this side, in this reaction, I can see that this cancels out, right? That'll be my intermediate. And then I get just N2 plus O2 plus Br2, which is what I was trying to get to eventually anyway. So you see, these are exactly the same equation. So you have to, if you get something like this to where you have two equations next to each other, and you have to get to a final one, such as this, then you're going to have to manipulate them. Sometimes you're going to have to multiply them by 2 to get the right number of products or reactants. So just be aware that you may have to multiply or swap switch products and reactants and put one over or put it to the power. So just be aware that there's multiple ways you can do this, okay? Now, the actual question says, find the case or equilibrium expression. Calculate the equilibrium constant Kp for this reaction. So we're actually trying to find Kp. These values, see, this is where they can trip you up. Look at my values. My values are given to me in Kc. So when I add, okay, so I added 1 and 3 together. I swapped the second one and created a number 3. Now I need to multiply these two values, these two Kc values for 1 and 3 together in order to get my Kc for the entire reaction. So let me go ahead and do that. So for one of them, I just kept it the same. Equation 1, I kept it the same, so I'm going to use the Kc value of 2.0. Now for equation 3 that we came up with on our own, we swapped products and reactants. That was Kc 1 over 2.1 times 10 to the 30, right? So in order to get my overall reaction for equation I just came up with, we're going to literally multiply these two together. 2.0 times 1 over 2.1 times 10 to the 30, okay? So that's going to be my overall Kc for this reaction, this two-step process. Okay, so there's my Kc. It is asking for Kp. Some people will just end up, so this is just my Kc. Some people just end up leaving it like that. Remember what I said. A lot of times it'll be really tricky. They'll give you Kc values asking for Kp. These are all gases, right? So it would only make sense that they were talking about pressures, but no, they gave you the concentration, so you need to find pressure. So again, we're going to use that expression we used last time. Kp equals Kc, all RT, delta N. So I'm not going to go into full detail of how we solve this again since I just did it, but I will write out 9.52 times 10 to the 31 is the Kc we just found, right? And then we're going to do that gas constant again, that 0.0821 or 0.08206. I just rounded because I'm running out of room, times that 298. In this case, they gave us a Kelvin of the temperature in Kelvin, and you always want it in Kelvin, so 298 K. And then we do the delta N, right? And the delta N value in this case for the overall reaction, remember, the overall reaction we found on the previous page was this, right? This is what we were aiming at. And it's going to be, delta N is going to be the product coefficients minus the reactant coefficients, total. Everything's always total. So it'll be 2 minus 3, which is also a delta N negative 1. So out here, you're going to have this Kc value, gas constant times temperature, and then a negative 1. So hopefully that makes sense. And we all have the answer keys now because I was actually the one that posted them. But I'll write the answer regardless. So if you're trying to solve this along with me or pausing because you're trying to solve, you'll actually have the answer right up here on the board. So moving on, and that's good, we're right at 30 minutes. We have number 5. The following gases are added to a 1 liter container. 2 moles, 3 moles, and it's generic. It says 2 moles of A, 3 moles of B. These gases react according to the reaction below. At equilibrium, the container contains this many moles of D. So this is when we first get into our basic, one of the most basic ice tables that you can actually get. Because they're not even really giving us molecules, right? They're giving us this reaction that is supposed to simulate molecules, right? A, B, C, D. and everything's gas, but I rarely write it because I run out of room like that. So, what indicates, so this is my first ice chart, what indicates that I need to use an ice chart? That's a big question a lot of people always have, right? So, what tells me that I need to use one? Well, in this question, it's fairly simple. Following gases are added to a container, a 1-liter container. 2 moles of A, 3 moles of B. These gases react according to the reaction below. At equilibrium, the container contains this many moles of B. So a lot of times, and the next question after this will actually be another good indication of what key words I'm looking for when I need to write out an ice table. So this one says the following gases are added. It gives me initial values. A lot of times they'll actually say, these are my initial concentrations, right? So that's a good indicator, is that they have an initial value and they say, what are my values at equilibrium? So let me write down a couple of keywords. Initial is a good one. And here it doesn't really say initial. It says these gases are added to a container. So my big key word for this problem in particular is that it says, it gives me like initial values, and then it says at equilibrium, at equilibrium, I actually have this value. I have these many moles initially, and then at equilibrium, I have another amount of moles, right? So that was my big indication. These are the two big words that you're going to be seeing. Think of seeing initial values, and then at equilibrium, we're going to have another value, a different value. So let's write this out. Everything's in gas, so gas phase, so everything's going to be in my ice table. C2D. So that's how I first write out everything that'll be in my equilibrium expression. And then I say initial, change, equilibrium. So that's my initial values, that's what the change, and that's what happens at equilibrium. So what do we have here? It tells me in the problem I have 2 moles. I have 2 moles of A. What are normally in ice charts? We normally only have either concentrations or, now this will change once you get into more complicated versions. You either have concentrations or you have pressures. I have these values in moles, so they need to be put into concentrations. And it says the following gases are added to a 1-liter container. So it says 2 moles, so I need to make it a concentration, so I say 1 liter. So lucky for us, this is all, this is all 1 liter. So all the values that they give us are exactly the same. Now there's 3 moles of B, 3 mole. And again, I'm going to put that over 1 liter to make it a concentration, because I either need to have a concentration or I need to have a pressure. Now, what about C and 2D? This is my initial concentrations, or initial pressures if we're dealing with pressures. Here are the concentrations. If these are initial values, just think of it this way. You haven't actually mixed these two together. I have A in one container, and I have B in another container. They have not mixed together yet, right? So if they have not even reacted yet, these are just my initial values in 2 separate containers, we don't have any products. Those are both my products. So we're going to assume that those are 0. Now here we're actually going to be able to get a change value, and this is why. It tells me at equilibrium, the container contains 0.4 moles of D. That means at equilibrium, I'm going to have 0.4 moles of D. And that'll be moles, again, over 1 liter. So it will be just 0.4 large m, right? 0.4 molarity, because everything's considered to be in 1 liter in this case. So very simple, very easy to follow. Now, what does that mean? That will give me my change. and then I will be able to fill in all equilibrium values. So what did I have to do here in order to get to 0.4? In order to get to 0.4, added 2 times, it says 2 times x. So in order to get to 0.4, I had to, so the change here is 2x. If we don't know what the change is, we always say it's x, right? But we will know what the change is because, so another thing I need to point out, everything on the product side will always be positive. Everything on the reactant side will always be negative, right? Because we are depleting we are depleting the reactants and we're forming the products, right? So I can find out what my change is in every case. This will be just x, right? 2x I got because of these coefficients out front. This will just be x. This will be minus 3x, and this will be minus just x. What can I can find out what my x values are by calculating this one right here. So this actually gives me my x value. That is saying 0 plus 2x is equal to 0.4. So that means that it'll just be 2x is equal to 0.4. So that just means that my x is equal to 0.2. So in each of these cases, I can say this is plus 0.2. So down here, my value is 0.2. So my equilibrium value for, maybe I should write lines in between so it doesn't get confusing. Yeah, that's probably a little better. So my equilibrium value for compound C or molecule C is 0.2. In here, we're going to say 3 minus 3 times that 0.2 value because we found out what x was. And this is going to give me 2.4. And all of these are moles per liter or molarity. Now I can say this 2 minus 0.2, which would be 1.8 mole, right? Or molarity, I mean. So when I have equilibrium concentrations, I can directly place equilibrium concentrations into equilibrium expression. If you forgot what an equilibrium expression is, it's, remember, Kc, equilibrium expression, is going to be your products over your reactants. So C, concentration of C, concentration of D to the 2, concentration of A, concentration of B to the 3. So when I'm plugging into Kc, I need to plug in, every time I find Kc, I plug in my equilibrium values. So this is what I plug into the Kc expression every single time. So that means I'm going to say 0.2 times 0.4 squared divided by 1.8 times 2.4 to the third. So hopefully that makes sense. That's how I find my Kc value, is from those equilibrium values. So I'm actually going to write that out for you. So just remember every single time that you're writing out these Kc expressions, the reason you're finding these equilibrium values, because that's what goes into an equilibrium expression, right? So hopefully it's all making sense to you now. And my final value for my Kc is that 1.28 times 10 to the negative 3. So just go ahead, try to plug those in, make sure you're typing it into your calculator right, and make sure you get the right answer, okay? So hopefully that's fairly straightforward for you guys. That is a basic Very, very, very basic, but it's just to show you, get you familiar with the concepts of the ice chart. Now this one is not my favorite, because this is where you actually have to write out. Number 6 is where you actually have to use the quadratic equation. I'm not going to do that fully because you guys should have learned that in math, but we will set this up for you. For the equilibrium, Br2 plus Cl2, 2BrCl. So this is my expression. Everything is in gases. So this is a good one because this is another good one to do because now we're going to use the quadratic. So this is all at 400 K. My Kc is equal to 7. Also important. If 2.5 moles of Br2 and 0.55 moles of Cl2 are introduced into a 3 liter container at this temperature, what will be the equilibrium concentrations? So again, what are my keywords that I'm going to use in ice chart? Okay, I have these being introduced, right? They're being introduced, which means initial. Those are my initial. So another keyword that we learned from here, introduced. And hopefully through mastering chemistry, you'll get really familiar with what terms, other terms they can use in order for you to determine that it's an ice chart that needs to be performed. So now, introduced was a big term, and then it says, what will the equilibrium concentration? So again, in this particular case, those are my key words that I am reading that I need to use an ice chart. So, for my ice chart, I'm going to say Br2, Cl2, 2, BrCl, right? And I'm going to say initial, change, constant, or equilibrium. Initial, change, equilibrium. And let me write these out like this so it's not confusing. Okay? So now it says I have this many moles in a 3 liter container. Br2 has 0.25 moles in a 3 liter container. Now I shouldn't have to explain that again, right? Because moles, 3 liter container. We need a concentration here. They either need to give us pressures or they need to give us concentrations. If they give me moles, I need to divide by however many liters there are. So again, there were 0.25 moles in the 3 liters. Cl2, they give me 0.55 moles in 3 liters, right? So hopefully you guys are following that. And then again, we haven't mixed these two together yet. So that means this is going to be 0. Now we're going to set up the change like we did before. We use the coefficients out front. Everything that's on the product side will be a plus. And everything that's on the reactant side, since we're getting rid of it, is going to be a minus. There's no coefficient out front there, and there's no coefficient out front there, right? So that's what my change is going to be. They did not give me an equilibrium value. They said, what will my equilibrium? Like in the last problem, they said they gave me an equilibrium value so I could figure out my change really, really fast. But in this case, they don't give me that. So I'm literally going to say this number minus x as my equilibrium. So this number divided by each other is 0.0833 minus x. So I'm going to plug that into my equilibrium values. And this number is 0.1833 minus x. And this is just going to be 0 plus 2x is just 2x, right? So now, a big indication that you will have to use the quadratic formula is when you have these equilibrium values with the x's and they give you the Kc value. So let's write out the equilibrium expression as if they were full numbers, like we always have been. My Kc is equal to products over reactants. Sorry, that's a little askew. And what is that whole thing equal to? So now, what do I need to do in order to use the quadratic formula? So basically what I'm doing is I'm trying to find this x. I'm trying to find this x so I can plug it in here and find my equilibrium values. So in order to use the quadratic formula, if you forgot how to do this in math class, I need to set this whole equation equal to 0. So basically I have to get everything on one side and set it equal to 0. So somehow I could, you could say this is, I shouldn't have to go through this, and I'm sure most of you know it, but you could like cross multiply, get everything so it's all, it's not a fraction like this. You could cross multiply and then divide the 2x on one side. Whatever you need to do. I'm not going to go through that math. Just work it out a couple times so you know for the test how to do it. But when you set the whole thing equal to 0, it should look like this. So that's the whole point of using the quadratic formula, is set the whole thing equal to 0. However you need to do that, whatever is the easiest for you. Oh, I think I said something wrong on the previous page. Right, you could cross multiply, get everything at, on one level, not as a fraction, so to speak. And then you could just subtract by this 2x on the other side, and then this whole thing will be 0, right? You don't divide. I think I said divide, you subtract. Anyway, regardless, you should know how to do the math, right? So now, once this whole thing is set equal to 0, I can use the x is equal to minus b squared Okay, so we all should know how to use that. This is A, this is B, this is C. Now, I think some people have emailed me and said, I cannot get that answer that you have gotten on your workshop. The problem is, I think you guys forget that when you plug in this value for B, everything needs to take on the proper signs. When you plug in this value for B, plug in negative 1.866. You will get the right answer. I've done it multiple times. And you can even, go online and do a quadratic calculator and plug it in and see it's the right answer. But you have to make this negative, right? So make sure that you have that negative. When you plug it in here, it'll be a negative times negative, make it a positive, right? So you have to plug it in like that. So I'm not going to go through this nitty-gritty, plugging stuff in. Make sure you do it in your calculator properly. Use the proper parentheses. And make sure you practice this a few times in your calculator so you get the right answer every time. Now, my x values will be this, or how do I know which value to use for x? Well, how I know is that if we look at my ice chart, oops. Yeah, here's the ice chart. So if I look at my ice chart, I need to have an initial value. So this was, it was 0.25 divided by 3. This was my initial value that was up here, right? So this value needs to be smaller than my initial value. Needs to be smaller than my initial concentration. So which one of these is smaller than that number, or that number, either one? This is obviously too big. So my initial concentration, this is smaller than my initial concentration. You can't have anything bigger than your initial, right? Make sense? Okay. So now, so that is not possible. So my x value is this. X is equal to 0.06385. Perfect. Now, what do I need to do? I need to actually take that value, plug it in here, and then plug it in to my KC expression. So, on a new piece of paper, let's actually go ahead and write that out. Since this one was a little bit more complicated, I will write what that fully looks like. So, that's going to be, so again, we have our products minus our reactants. So that's going to be the 2x 0.0833 minus x, and then 0.1833 minus x. So my x values are going to be plugged directly into there. So everywhere you see an x, you're going to plug in that 0.06385. Oh, 2x squared, right? Because it's products with its coefficients out front. I should have done that over here too, hopefully. Yeah, 3x squared. Yeah, okay, we're good. So on that page, our KC expressions, remember, we always have to put that coefficient that's out front in the expression, and the actual equation also needs to be a superscript, right? So don't forget to do that. You also have to say, even in your ice chart, remember, in the ice chart, you even have to put that coefficient out front. So you count for it almost twice, so don't get confused. Coefficient out front of that, BRCl, bromium chloride, it had a 2 out in front of it in the actual full-on equation. So that means it's a 2x and raised to the 2. Okay? So anyway, I plug that in. My x is in there. And then my KC expression, or value. Oh, wait, KC is always 7. Right, so this is equal to 7, so we don't solve for x, we don't solve for that at all anymore. We just find actually what our, so for BR2, it's not asking for the KC at equilibrium. It's actually asking for the concentrations, the equilibrium concentrations of each single molecule. So for BR, we just say that. So for BR, my answer, once I plug in that value right there, BR2 is 0.01948. And then when we do CL2, we just take that those equilibrium column that we created. And that one, once we plug in that value, is 0.11945. Then we do the exact same thing for BRCl. BRCl will be just that 2x, right? So then we just say 2 times that x value. 2 times that. And that's going to give me that 0.1277. Okay? So hopefully that makes sense to you. I started plugging into the actual equilibrium expression, but what it asked for in this problem, you didn't have to actually write that out. But what it actually asked for in this problem, what were the equilibrium concentrations of each of the molecules at the very end of the reaction. So I just plugged in for BRCl and BRCl. So right here, you just plug in those equilibrium values, whatever, when you find your x, and you can say, oh, my equilibrium for BRCl is 2 times that x value. Cl2, that number minus the x value we found, and that minus the x. And the only other trick is that when you find 2 different x's, you have to make sure that this value is smaller than your initial concentrations, okay? So hopefully that made sense. And that was getting kind of messy. But the biggest portion here, this you didn't really need to do, right? this is what you needed to do to find your answer. Okay? So now, that took up most of our time because those ice tables take forever. But we should be able to go through 7 and 8 just fine. And then hopefully, if you have any problems with number 9, number 9 is just kind of a practice thing. You need to practice knowing how things shift, Le Chatelier's principle, right? How things shift when you take them out. So that's more of memorization and practice. So we'll make sure to go through number 7, and then we'll be done for the night. And I will upload this. So, number 7. Quickly, how does a reaction quotient different from an equilibrium constant? That's something I'm just going to let you guys read through. If Kc, so this is what you'll need to know for number 8. If Kc is less than QC, if QC, this is what it says. Sorry, it's getting late, I'm tired. QC is less than Kc, which direction will the reaction proceed to reach equilibrium? So if we solve for this, so that's something you need to solve for normally, it's going to move towards products. Or you can also say to the right. So again, just kind of a memorization thing. You can solve for it, and we will in the next problem. What condition must be satisfied so QC equals Kc? If they equal each other, then the system is at equilibrium. So, that just means the system's in equilibrium. That's all there is to it. Now, we're going to do number 8 and solve for that. Okay? So now, this is where we find QC versus Kc. At 100 degrees C, equilibrium constant for the reaction. And they give us this reaction COCl2, CO plus Cl2. The equilibrium constant has a value, so it's giving me a Kc value. Are the following mixtures, all these molecules, at 100 degrees C at equilibrium? If not, indicate the direction that the reaction must proceed to achieve equilibrium. So, they also give me these concentrations in this problem. COCl2. For some reason, people get very confused by these, and it's actually a very simple, very simple math. And a lot of times they use different values, but you're doing exactly the same thing. So I understand how sometimes the variables can get confusing, since a lot of times they mean the same thing. So basically, QC and Kc are basically the same thing. You calculate for them almost entirely the same way. The only reason they use QC is basically just to change that variable when you're calculating for it. So you're basically calculating for Kc, but you're calling it QC. I don't know if that, excuse me, hopefully makes a little bit more sense to you guys, but they give me in this problem a Kc value, right? They're giving me this value, and maybe I can actually just move these papers up so I can just write below it so we have all these values to work with. Yes, okay. Okay, good. Actually, you can see all that. Perfect. So now, I'll work down below it. Now we have all of these values, and we're just going to calculate as if it was already Kc. We already have a Kc value, but now they're giving us these concentrations. We're going to call it QC just so it is a different variable than Kc. Okay? So don't get confused. It's calculating the exact same way. So many people get confused by that. So anyway, here we have these values. Let's set it up, and we'll just call it QC. Because we already have a Kc, so we're just going to call it a different variable. What do I do for Kc? I say products over reactants. What do I always do, right? This is normal. We've done this 1,000 times. So this shouldn't be any different, right? So now, I just plug in all of these values that they gave me, just like it was Kc. So it should be very, very simple. Everything should be exactly the same. So CO is just that 3.3 carbon monoxide times chlorine gas, which is that 6.62 times 10 to the negative 6. And then over that value. And everything in the reaction has a 1 out front, so we didn't need to raise anything to any power. Pretty simple, right? So now, what did I find out my QC to be? My QC, which is calculated the same way Kc is. And now we directly compare QC to Kc. This one, QC is bigger than Kc, right? -8 is bigger than -10. So if Q, hopefully we can still see this, okay. Q, I'm trying to put it in right here. Q is greater than K, then it's going to be the reverse of what I said previously, because the reverse was Q was less than K. If Q is greater than K, it is going to, the reaction will proceed towards the left, so towards the reactants. You can say reactants or left. And the reverse, I'll move that up. Okay, maybe not. So you can say if Q is greater than K, the reactants, in order to achieve equilibrium, it's going to move towards the reactants or it's going to move towards the left, okay? So that is all we have time for today. I went about 2 minutes over, and then hopefully someone can help you with number 9 if you do not fully understand it. But I mean, the ice charts are really difficult. So hopefully this this video helped you, and hope you guys have a good night and you enjoy these videos and find them very helpful. All right, and hopefully maybe or maybe not we won't have school tomorrow. So all right, guys.